Ancient Egypt has fascinated researchers for centuries, not only because of its pyramids, temples, and colossal statues, but because of one question that refuses to disappear. How did a civilization that existed thousands of years ago cut and shape some of the hardest stone on Earth with such astonishing precision? For generations, historians believed they understood the answer. Copper tools, stone pounders, manpower, and endless labor were considered sufficient explanations. Yet, as modern technology advanced and engineers began examining ancient artifacts more closely, cracks started appearing in those traditional theories. Then a new wave of analysis emerged, including investigations assisted by advanced artificial intelligence systems, such as Grok AI, which examined archaeological data, tool marks, measurements, and construction evidence from ancient Egyptian sites. The conclusions were not what many researchers expected. The mystery begins with granite itself. Granite is one of the hardest natural stones commonly found on Earth. It contains large amounts of quartz, a mineral significantly harder than copper. This creates an immediate problem for traditional explanations. If ancient Egyptians primarily used copper tools, how were they able to cut, shape, drill, and polish granite with such extraordinary accuracy? Across Egypt, especially in sites associated with the Old Kingdom, enormous granite blocks weighing dozens of tons display surfaces so smooth and precise that they continue to astonish engineers today. Some artifacts contain straight lines, sharp angles, and symmetrical features that appear difficult to achieve even with modern equipment. One of the most famous examples can be found inside the Great Pyramid at Giza. The king's chamber contains massive granite blocks transported from quarries hundreds of kilometers away. Each block weighs several tons. The precision with which these stones were fitted together has fascinated visitors for centuries. Yet transporting the blocks represents only part of the mystery. Before they could be moved, they had to be extracted, shaped, and finished. The evidence left behind at ancient quarries suggests a process far more sophisticated than simple hammering with stone tools. Researchers examining unfinished granite monuments discovered something unusual. Many surfaces contain marks that appear remarkably consistent. Instead of random impacts expected from primitive shaping methods, certain areas display patterns suggesting controlled cutting operations. Circular grooves, parallel striations, and smooth internal surfaces have been documented at multiple locations. Some engineers studying these features concluded that the marks resemble the results produced by rotating cutting devices or advanced drilling techniques. The discovery of ancient granite core samples intensified the debate. These cylindrical stone cores were recovered from archaeological sites and appear to have been produced during drilling operations. When modern engineers measured the spiral grooves visible on some cores, they found something surprising. The groove progression suggested drilling rates that seemed difficult to reconcile with simple copper tools operating against extremely hard granite. According to some analyses, the penetration rates implied a level of efficiency that challenged traditional assumptions about ancient technology. As discussions intensified, researchers began collecting enormous amounts of data. Measurements from quarries, unfinished obelisks, stone cores, statues, sarcophagi, and temple structures were compared using increasingly sophisticated methods. This is where artificial intelligence systems entered the conversation. Grok AI and similar analytical platforms were tasked with examining patterns across large archaeological datasets. Rather than approaching the problem from historical assumptions, the systems focused on evidence, measurements, material properties, and engineering constraints. One question repeatedly emerged. If copper alone was insufficient for cutting granite efficiently, what additional methods may have been employed? Archaeologists have long suggested the use of abrasive materials, such as quartz sand. In this theory, copper tools acted primarily as carriers for abrasive particles. The actual cutting occurred because the harder quartz grains ground against the granite surface. This explanation solved some problems, but left others unresolved. Certain artifacts displayed levels of symmetry and precision that still appeared remarkable even when abrasive techniques were considered. The discussion became even more interesting when researchers examined ancient Egyptian sarcophagi. Some granite sarcophagi display internal surfaces that are extraordinarily flat and smooth. Sharp internal corners appear in locations difficult to access using simple hand tools. Measurements taken from several examples revealed tolerances that impressed modern machinists. Grok AI reportedly identified recurring geometric consistency across multiple artifacts, suggesting standardized production methods rather than purely manual craftsmanship. The findings did not prove advanced lost technology, but they indicated that ancient Egyptian stoneworkers possessed techniques more sophisticated than many people had assumed. Attention soon turned toward the unfinished obelisk at Aswan. This enormous monument remains attached to bedrock in the quarry where workers abandoned it after cracks appeared in the stone. The unfinished obelisk provides a rare opportunity to study ancient extraction techniques directly. Researchers observed long channels cut around the monument and evidence of systematic stone removal. Traditional explanations emphasize the use of dolerite pounding stones, which are harder than granite and capable of gradually shaping it through repeated impact. Thousands of such stones have been found at quarry sites, providing strong evidence that pounding played a major role in Egyptian stoneworking. However, Grok AI's analysis highlighted an important point. The existence of pounding stones explains certain stages of shaping, but may not fully account for final finishing operations observed on completed monuments. The evidence suggested a combination of techniques rather than reliance on a single method. Rough shaping, fine cutting, grinding, polishing, and finishing may each have involved different tools and procedures optimized for specific tasks. Another mystery involved transportation. Massive granite blocks weighing tens of tons had to be moved from distant quarries to construction sites. Conventional explanations emphasize sledges, lubricated pathways, human labor, and river transport. Experimental archaeology has demonstrated that large stones can indeed be moved using such methods. Yet Grok AI's evaluation of logistics data revealed the extraordinary organizational complexity required. Quarry operations, transportation networks, workforce management, and construction planning would have needed levels of coordination rivaling major modern engineering projects. The more evidence researchers examined, the clearer one fact became. Ancient Egyptian builders were not merely laborers following simple procedures, they were highly skilled engineers, craftsmen, planners, and organizers. Whether using copper tools, abrasive sands, stone pounders, or combinations of multiple technologies, they achieved results that continue to impress experts thousands of years later. The debate intensified further when precision measurements of certain granite artifacts were compared against modern manufacturing standards. Some researchers argued that the observed precision indicated machine-like capabilities. Others countered that exceptional craftsmanship can achieve extraordinary results without advanced machinery. Grok AI's assessment reportedly avoided extreme conclusions. Instead, it emphasized that the available evidence strongly supports a level of technical sophistication often underestimated in popular discussions of ancient Egypt. Perhaps the most important contribution of AI analysis was not providing a definitive answer, but identifying weaknesses in oversimplified explanations. For decades, discussions tended to divide into two camps. One side insisted that conventional methods fully explained every artifact. The other argued that unknown advanced technologies must have existed. By analyzing large amounts of evidence without ideological attachment, AI systems highlighted the possibility that reality may be more nuanced. Ancient Egyptian stoneworking likely combined remarkable human skill, extensive experience, specialized tools, abrasive materials, and highly organized labor systems, operating at a scale rarely appreciated today. As researchers continued examining quarry marks, drill cores, unfinished monuments, and completed structures, the mystery remained unresolved. Each new discovery seemed to answer one question while raising several more. How exactly were the finest surfaces achieved? What specific techniques produced the most precise features? Were certain methods lost over time? And why do some artifacts appear significantly more advanced than others? The answers may still lie hidden within Egypt's deserts, temples, and quarries. Every measurement, every tool mark, and every unfinished monument provides another clue in a puzzle that has fascinated historians, engineers, and archaeologists for generations. With artificial intelligence now joining the investigation, researchers are uncovering patterns that were previously impossible to detect. Yet despite all the technology available today, the ancient craftsmen who shaped granite thousands of years ago continue to guard many of their secrets. As the investigation into ancient Egyptian granite cutting techniques deepened, the discussion moved beyond individual artifacts and isolated quarry sites and began focusing on a much larger question that challenged the foundation of historical engineering: assumptions. The real mystery was not only how the Egyptians cut granite, but how they maintained consistency, precision, and scale across thousands of massive stone structures over centuries without leaving behind a clear and complete record of their exact methods. While traditional archaeology explains much of the process through copper tools, stone pounding techniques, and abrasive materials, the emerging AI-driven analysis introduced a broader perspective that considered system-level organization, material efficiency, and engineering behavior patterns across multiple sites simultaneously. One of the most striking areas of focus was the unfinished and partially completed stonework found throughout Egypt. These sites act like frozen snapshots of ancient construction processes, preserving tool marks and work stages that completed monuments no longer reveal. Grok AI's analysis of these unfinished surfaces reportedly identified recurring structural patterns that suggest a highly standardized approach to stone shaping. Instead of random or purely manual variation, many quarry surfaces display consistent geometric behaviors, as if ancient workers were following well-established procedural steps that minimized material waste and maximized accuracy. At several quarry locations, long parallel grooves carved into granite blocks suggest repeated controlled actions rather than irregular hammering. These grooves vary in depth but maintain surprising alignment across large surfaces. In traditional interpretations, such markings are explained as the result of repeated pounding with dolerite stones combined with abrasive sand. While this explanation remains widely accepted, the consistency of the patterns has encouraged further analysis. Grok AI's pattern recognition reportedly highlighted that similar groove structures appear in geographically distant quarry sites, which raises questions about knowledge transfer and standardized working methods across different Egyptian regions. Another major focus of study involves the famous granite obelisks, many of which were never completed or transported. The unfinished obelisk at Aswan remains one of the most important archaeological sites for understanding ancient stoneworking techniques. Carved directly into bedrock, this massive structure shows clear evidence of systematic excavation. Workers had already removed large sections of surrounding stone, shaping the obelisk with remarkable precision before a fatal crack forced abandonment of the project. Traditional analysis suggests that teams of workers used dolerite pounding stones to gradually chip away at the granite, but the efficiency required to carve such an enormous structure in a relatively short period continues to raise questions among engineers and researchers. Grok AI's comparative analysis of excavation speed, estimates, and tool wear patterns introduced a new layer of interpretation. By evaluating the expected degradation rates of dolerite tools against the volume of granite removed, the system reportedly identified potential gaps in efficiency models. This does not imply unknown technology, but it suggests that ancient workers may have used optimized sequences of operations, combining different materials and techniques in ways not fully reconstructed today. For example, pre-fracturing methods, heat treatment of stone surfaces, or strategic use of water and abrasive slurry could have significantly increased the effectiveness of manual tools. Attention also turned toward the internal geometry of completed granite artifacts. Some sarcophagi and architectural components display internal corners and surfaces that appear unusually precise given their material hardness. Modern machinists studying these objects have noted that certain features resemble outcomes produced by controlled cutting and grinding processes. Grok AI's evaluation of dimensional consistency across multiple artifacts suggested that there may have been a form of standardized finishing tolerance used by ancient craftsmen, even if that tolerance was achieved through manual rather than mechanical means. This idea challenges the assumption that precision engineering is exclusively a modern development. Another important element in the discussion involves tool mark evolution across different historical periods of ancient Egypt. Evidence shows that early stoneworking phases relied heavily on direct percussion techniques, while later periods exhibit more refined surfaces and improved finishing quality. This progression suggests continuous technological refinement rather than sudden innovation. Grok AI's timeline-based analysis reportedly identified gradual improvements in surface smoothness and dimensional accuracy, indicating that knowledge was likely passed down through generations of craftsmen who continually improved methods through experience and experimentation. The role of abrasive materials remains central to most explanations of granite cutting. Quartz sand, being harder than copper, is believed to have played a critical role in grinding stone surfaces. In this process, copper tools acted more like carriers or guides rather than primary cutting instruments. When combined with water or oil, abrasive slurry could significantly increase material removal efficiency. Experimental archaeology has demonstrated that such methods can indeed shape granite over time, although the process requires immense labor and patience. Grok AI's analysis supports the idea that abrasives were essential, but also suggests that their application may have been more systematically controlled than previously assumed. Transport logistics also emerged as a key factor in understanding ancient Egyptian engineering capabilities. Moving multi-ton granite blocks from remote quarries to construction sites such as Giza required careful coordination of manpower, waterways, and seasonal planning. Evidence suggests that Nile River transport played a major role in moving heavy materials, especially during flood seasons when water levels were high enough to support large barges. The precision with which some stones were delivered and installed indicates that transport and construction phases were closely integrated within a unified planning system rather than being separate stages. Grok AI's system-level modeling reportedly highlighted how interconnected these processes must have been. Quarry extraction, shaping, transport, and installation could not have operated independently if efficiency and precision were to be maintained at such a large scale. Instead, they likely functioned as coordinated components of a highly organized engineering network. This interpretation aligns with archaeological evidence, showing administrative records, workforce organization structures, and standardized construction practices across different dynastic periods. Despite all these insights, one of the most important conclusions emerging from modern analysis is that ancient Egyptian granite cutting does not require unknown or lost advanced technology to explain its achievements. Instead, it suggests an extraordinary combination of human skill, long-term knowledge development, material understanding, and large-scale organization. The apparent mystery arises not from impossible techniques, but from the difficulty modern observers have in fully reconstructing cumulative knowledge systems that evolved over thousands of years and were passed down through generations of craftsmen. However, what makes the Grok AI contribution particularly significant is its ability to analyze patterns across vast data sets without being influenced by traditional assumptions. By comparing tool marks, dimensional data, and material properties across hundreds of artifacts and sites, it can highlight correlations that might otherwise remain unnoticed. These correlations do not replace archaeological interpretation, but instead enhance it by providing new perspectives on how ancient engineering systems may have functioned at scale. As the analysis continues, new questions emerge rather than clear final answers. Were certain techniques restricted to specialized guilds of craftsmen? Did regional differences in material availability influence variations in cutting methods? How much knowledge has been lost due to time, environmental degradation, or incomplete archaeological recovery? And most importantly, how close are modern reconstructions to fully capturing the reality of ancient Egyptian engineering practice? The evidence continues to build a picture of a civilization capable of extraordinary engineering achievements through a combination of persistence, ingenuity, and deep practical understanding of materials. Whether using pounding stones, abrasive sands, carefully controlled cutting sequences, or advanced organizational systems, ancient Egyptian builders managed to shape one of the hardest natural stones on Earth with a level of precision that still commands respect today. As Grok AI and other analytical systems continue examining archaeological data, the story of Egyptian granite cutting remains an evolving investigation. Each new insight adds clarity to certain aspects while opening new layers of complexity in others. The ancient builders who once worked under the desert sun may never have imagined that thousands of years later, their tool marks and stone surfaces would still be studied in such detail. Yet those marks remain, silently preserving the record of a lost engineering world that modern science is only beginning to fully understand.